and then we cross our fingers and see if it works. And there we go. We have some terrain. Hello, and welcome to a new series. This is one that's been requested quite a lot. Not surprising, really. Most of the people who subscribe to me are here for Minecraft, and there is a lot of crossover between Minecraft and 7 Days to Die. But this is a series, much like the Minecraft series, on how to make a game like 7 Days to Die. For people who don't know what 7 Days to Die is, it is a game that is still in alpha, but is very popular, and it's kind of like, you can think of it as like Minecraft, but R-rated. It's got the destructible terrain and the building blocks and stuff like that, but it's set in an apocalyptic world and there's zombies, and every 7 days all the zombies come and try and eat you. So this series is going to be about that. Now I've got a few caveats before we get into the series. If you're not bothered about the caveats, if you just want to get straight into the tutorial, you can skip to this time. Okay, so caveat number one. As I'm recording this, it is 3 days after Bonfire Night in the UK. Bonfire Night is when everybody sets a lot of fireworks off. So I'm not sure how much of that noise is making its way through the microphone, but if you hear banging in the background, it's that. Unfortunately, Bonfire Night in the UK now apparently is a week-long affair. So unless I decide to not record another video for a week or so, it's just going to have to be something we're going to have to get through. Second thing is, for all those aforementioned Minecraft people, don't worry, the Minecraft series is not over. I've fairly consistently put out like 4 videos a month for the better part of a year now, and Minecraft is typically on average 2 to 3 of those videos. That's not going to change. Onto the series itself, I'm not claiming that the way I do this is the way that Fun Pimps, who make 7 Days to Die, do it, and I'm not claiming that this is the best way to do it. This is just the way that I would do it based on my knowledge, which I will admit up front is far from comprehensive, and based on playing the game a lot. So I have no special inside knowledge about how Fun Pimps have designed their game or how they code things. If somebody like Brackies decided to do how to code a game like 7 Days to Die, it would absolutely be better than mine, technically and production-wise. But as far as I know, they're not doing that, so you're stuck with me for the meantime. And then the last thing I want to point out is that, unlike the Minecraft series, where I can pretty much get away with making my clone look identical to Minecraft, because, let's face it, it's just blocks with 16-pixel textures. Even if Microsoft decided to send me a cease and desist because I'm using the actual textures from Minecraft, it would still look a lot like Minecraft if I used a third-party texture pack or made my own. This is different. These are using proper models and textures, and I can't rip them from the game. If the video got enough views, I would almost certainly be getting in trouble with Fun Pimps. So where we can, we'll make assets, but I'll be honest, I am not an artist or a 3D modeler, and it would not do the tutorial series justice if I was to try and make the models for this game or the animations or the textures. So I'm going to try and use as much as I can out of the asset store, and wherever possible, it will be free assets. I want it to be stuff that you guys can also download. Right, we're going to start off with marching cubes. Now, I don't know how many of you have heard of marching cubes. I know I've mentioned it to a couple of people who've asked me in Discord how to do 7 Days to Die. And basically, marching cubes is another type of voxel management system, I guess you could call it. Unlike Minecraft, where you have blocks, and a block is either there or is not there, marching cubes samples the corners of the cube. So, one second. So we have a cube of sorts. Yeah. So yeah, Sebastian Legge has a great tutorial or a great overview of what marching cubes is. Not necessarily heavy on the code on how to do it, but he just supplies source code for how he did it, and he explains the concept of what it is. But basically, you have these, it doesn't sample the cube itself, it samples the corners, and it says, say, this corner inside the terrain or outside of the terrain? Is this one inside of the terrain or outside of the terrain? And then depending on the results, it draws a particular mesh inside the cube. So there are 8 corners, obviously, and the total amount of combinations you can have, configurations of various corners being inside and outside of the terrain, comes to 256. So there are 256 possible combinations for how you can have a particular cube. What you can do is, at any point, you sample the 8 corners of the cube, you get the configuration that it represents, and then you put that mesh in place, and you can create a 3D model this way. So like every tutorial you'll probably find on the internet for marching cubes, I have not created my own table. I have stolen them from the internet. I'll provide links to 5 or 6 different resources that I used when I was working through this tutorial. So basically we have a corner table, which is just the corners of the cube. So you got your bottom left, bottom right, etc., front, back, top, bottom. That's just the corners of the cube. And then we have this edge table. So the edge table, each one of these represents all the edges of the cube. There's 12 edges of the cube. And what we're going to do is we are going to be checking between these edges to see if one of them is inside the terrain and one of them is outside of the terrain. So if you imagine your terrain is passing through our cube, and it goes halfway through the cube, the bottom corners are going to register as inside the terrain and the top corners are going to register as outside of the terrain. Therefore, it will intersect the edges that go up from the bottom to the top, or from the top to the bottom, whichever way around it goes. And then from that, we can tell that it intersects those edges. Now, the table that is the most laborious is the table of configurations. So these are the triangle indexes. You ready for this? There we go. So as you can imagine, I wasn't very keen to create this myself, but basically these are the triangle indexes that represent the verts in, I think it's either here or here, one of these two. I'm pretty sure it's this one. And each one of these represents one of the configurations. What we're going to do to start with is I'm going to show you the configuration, so it might be a bit easier to visualize. So the first thing we'll do is we need to make a few, well, first thing we'll do is collapse that actually, is we need to make a few functions to deal with our meshes. So the first thing we need is a few variables, or lists in this case. Vector 3, anyone who's done the Minecraft series will recognize some of this. Hopefully we're not going to be going over too much ground that I've already covered in other videos, but some parts of it are unavoidable. And then we're going to create a few functions to deal with these. So the first one is void clear mesh data. And then the next one is just going to be build mesh. This is going to hold the vertices and the triangles, obviously, for the mesh that we're going to create. This clears those two lists. And then in here, we are creating, when we're making sure we put void before it, we are creating a new mesh, and then we're going to assign these lists to it. So mesh.vertices equals vertices.toArray, because we are storing it in a list, and you can't pass a list into an array without converting it, and that's what toArray does. And then mesh.triangles equals triagonals. And then we're just going to try and keep everything nice and neat. Recalculate normals. And then finally, we need a mesh filter. So up here, mesh filter. And then we can set the mesh for that mesh filter. Shared, is it shared mesh? Just mesh. And then what we'll do is we will grab our mesh filter in start. Now if I go back into here, you can see that I already have a marching cube object. I haven't done anything to it. It's an object that's got a mesh renderer and a mesh filter, and it has our script here. I can get rid of that mesh collider, we don't need that. So let's do the code to actually show us something. So we're going to need a int variable, which we're going to call config index. And then if we just collapse all these just to make things a bit easier to follow, and we'll put it here, we're going to create a new function called marchCube. It's going to take in a vector 3, which will be the position of the given cube. And it's going to take in an int, which will be the configuration index. The configuration index is the index that we are using out of this table, this huge, enormous, ridiculously large table here. So the first thing we want to do, and when you, if you check out the code that I will put in the link, that I'll put a link in the description to all the code. If you check out that code, I'm going to heavily comment that code. I'm not going to do it in the video because that just means more of you watching me fumble at the keyboard, mistyping stuff. So the first thing we want to do is we want to say if config index is equal to 0 or config index is equal to 255. Now that is the first. As you can see, there are no triangles there. Sorry, I'll clear up. -1 is our way of telling us later on in the code that we are done. Because obviously there is a maximum of, I think, is that 16? I think 16. There's a maximum of however many this is, 16 I think, triangles that there can be in a given cube, but it's not always going to be that many. So in this case, there's 3 in this one, there's 5 in that one, or 6, sorry. And then basically the -1 is a way of keeping track of when we're actually done. We can go through 0, 8, 3, -1. Okay, we've hit -1, that's the end. So the first one is all -1s, there's nothing there, and then the last one is all -1s, there's nothing there. Now what that means is that either this cube that we're looking at, all of its corners are either completely below the terrain, in which case we don't need to draw it, because we don't want to be drawing objects that you can't see because they're inside the terrain, or they're completely outside of the terrain, in which case you don't want to be drawing it because it's air, essentially. So first thing we do is we check that, and if either of those conditions are true, we can just return. There's no point in doing anything else. So the next thing is we loop through our triangles. We're going to get an edge index, which is going to equal 0. And then we're going to loop through int I equals 0, I is less than 5. There are never more than 5 triangles in any of these meshes, so we never need to loop more than 5. I plus plus. And then inside that loop, we need another loop, which I'm just going to use p. The I and the p are completely arbitrary. You can call them whatever you want. Equals 0. P is less than 3, because there are never more than 3 points in a given triangle. P plus plus. Now inside here, we first want to get the, we're going to call it indis. We want to get the current index that we're working with. So we get that by looking up the triangle table. We're going to get the configuration index, which is, for the minute, it's this value that we're going to pass in here. And then we want the edge index. The configuration index tells us which one of these we're using. And then the edge index tells us which number in that one we're using. So if we passed in 3 and 2, that would be 0, 1, 2, 3, and then 0, 1, 2 would be returning this. So that's how that works. Then the next thing we want to do is if indis is equal to -1, as I said before, that means that we're done. We're finished with this triangle table, and we can, again, just return. So now we need to get actual positions. So we need 2 verts for this, which we're going to call vert1 and vert2, and they're going to equal position plus edge table, and we'll pass in the indis, and then just 0. So if you remember, these represent, the edge table represents the start and end point of a given edge. So we have the indis, which tells us which of these we're using, and then we have 0 and 1. Like we have this one, and then we have this one. So then vert2 is the other end of that edge. So now these two, vert1 and vert2, represent the start and edge of a cube. So I've just had a slightly more serious attempt at drawing a cube. So if you imagine we're looking at this edge here, this would be V1, for example. It might be the other way around, and this would be V2, or like I say, this could be V1 and this could be V2. But basically we are getting this point and this point, and then the next thing we do is we want to check if the values, if one of the values is below the surface and one of them is a bit like as in inside the terrain and one of them is outside of the terrain, then we know that our terrain cuts through that point there. So to do that, we're going to say vector3 vert position equals vert1 plus vert2 divided by 2. And that gets us the midpoint between those two verts. And then finally, vertices.add, and we're going to add vert position. And then triangles.add. Oh, we're going to remember to put semicolons in. And then triangles.add, and we're going to give our vertices.count -1, which means we're getting the index in the vertices list, sorry, of the last thing we added, which is this. And then the last thing we want to do in this function for now is increment edge index. And then that will keep going until we hit the end of the given triangle table. Now to actually demonstrate this, we're going to go into our update. We're going to create an update. And we're going to say if input.get, don't forget your brackets, kids, input.get key down. And we'll just say, we'll use spacebar. We will increment config index. We will clear mesh data. And then we will march cube. And we'll just give it vector3.0, pass in our config index, and then we'll build our mesh. And we're going to set this to -1 so that the first time we run this function, we're going to be getting 0. So let's give that a whirl and see what happens. So I press spacebar once, we get nothing because the first index that we're looking at is 0, and 0 is, I can't remember if it's in the air or inside the terrain, but either way it doesn't render anything. But if I press it again, we get our first configuration, which is just a triangle. And then obviously we've probably got a lot of triangles. This one is a slope of kinds, and then I can just keep going. We can see all the different configurations, and these don't look like much now, but when you put them together they do. So yeah, that's just to show you what I mean by the configurations. All these represent a different configuration of a cube and where its corners are. So now let's make it show something a bit more meaningful. So we're going to go up to the top and we're going to add a few necessary values. The first one, float terrain surface equals 0.5f. We'll explain that one shortly. Int width equals, we're going to say 32. Int height equals 8. These are just the width and height in cubes, so this is the amount of cubes that we're going to, quote, march through. And then we need a float array, 3-dimensional, which we're going to call terrain map. And that's going to store our values so that we can sample them when we actually draw our mesh. So if we just go down below update, we're going to create a new function called void Populate Terrain Map. And then in here we need to loop through all the different positions. Now, I don't know how to explain this without a visual aid. So when you're doing something like Minecraft and you're just sampling blocks, it's fairly straightforward. You have your width, and then let's say we have a width here of 4. This would be block 0, this would be block 1, block 2, block 3. However, we're not sampling blocks, we're sampling corners. So even though we have 4 cubes, quote cubes, we actually need more than that in points to sample, because we've got 0.1, 0.0, sorry, 0.1, 0.2, 3, 4, 5, 6. That's how many points we need to sample. However, unlike this drawing, these points are shared. So we don't need to worry about shared points, so we can just say 1, 2, 3, 4. However, that is 1 more than the amount of cubes that we are looking at. So when we do our loop through, we need to factor in that extra 1. So for int x equals 0, x is less than width plus 1, x plus plus. And then we'll just copy this and change it for y and z. And then don't forget to change the y1 to work with the height and not the width. And then we'll go up to our start, and we want to declare this array. So terrain map equals new float, and then we want width, height, width. So into here. The first thing we want to do, because of the way we're doing that, for now we're just going to work with plain terrain. We're not going to worry about 3-dimensional terrain, as in like caves and things like that. We're just going to get a terrain surface going. So we want to get the height at the given x and z coordinate. So we'll say float this height equals float. We want our height value, but we want it recast as a float because we're going to be timesing it by a float, multiplying it by a float. And then we're going to multiply it by, we're going to get a Perlin noise value. So if you remember, or if you haven't worked with Perlin noise before, Perlin noise gives you a value between 0 and 1. So you can use that essentially as a percentage modifier, because I've said this before, but if you times 10, for example, by 0.8, you get 8. If you times 100 by 0.25, you get 25. It kind of works like a percentage thing. So this is going to give us a value between 0 and 1, and we're going to times our height by it, and that will give us the height of the terrain at any given x and z position. So mathf.Perlin noise, and again we want to recast it, because if you pass integers into Perlin noise, it gets funny. I think it returns the same value over and over again regardless of what numbers you actually give it. So recast it as x. We're just going to randomly divide it by 16. These numbers are completely arbitrary. I basically just messed around with the numbers in preparation just to get something that gives terrain that you can look at on the screen. So there's absolutely no rhyme or reason to these numbers. They just give something that works for this video. And then we're going to add 0.001 for the same reason as we're not passing in an int. It can get weird if the numbers are whole. So just to avoid the possibility of the numbers being whole, we're just going to add this random 001 number. And then exactly the same for the z position. So that gets us our height value. So we're going to create a new value next called point. And we'll set the value of that to 0. And now this is where it gets a bit tricky. So terrain surface, which we declared up here, and kind of think of it as like a density, I guess would be a good word. So if you imagine the terrain goes through like that, this is 0.5, and then this will be 1, and this will be 0. If it's 0.5, it is bang on the terrain, and you can change this value here, and it would change the shape of the terrain, or the density of the terrain. What we want to do for each one is we want to check where the given point is in relation to the terrain. So if y is less than or equal to this height minus 0.5, then that means that it is well and truly in the terrain. It's in solid ground. We're not bothered about it. Well, it's not that we're not bothered about it, it's that we're not bothered about the density of it. It's far enough into the ground that it doesn't matter how far away it is from the actual terrain surface. So we're just going to, if it's less than that, we're just going to set it to 0. However, if y is greater than this height plus 0.5, that means that it is far enough above the terrain that, again, we're not bothered. It doesn't, once you get above 0, like below 0 or above 1, it doesn't matter how far away from the terrain it is, because it's just either solid or air. So in that case, we set point to 1f. Now where it gets a little bit trickier is if it is within that range, if it is above 0 and below 1, with obviously the terrain being in the middle, 0.5. So we're saying else if y is greater than this height. So bearing in mind that we're using else if, so we've already checked, if we get to this if statement, we already know that it is not less than this height minus 0.5, and it is not greater than this height plus 0.5. So now we know that it is within a range of one float of this height. So we're only interested in whether it's greater than this height or less than this height. If it's greater, then point equals, we'll recast y because it's an int, remember, minus this height. And then if it's not, if it's less than, then we're going to set point to this height minus recast y again, float y. Basically what that does, we just go back to my magical paint board. So if you imagine we have a stack of blocks, currently we have our height set to 8, so this would be 8 high, and our terrain surface goes here. Now we are interested if the terrain surface, so say this is 0.7, then the density value of these is, I think this one would be 0.3 or 7. one of them will be 0.7 and one of them will be 0.3. Let's just assume it's this way. And then we can use that value later. We're not going to do it in this video, but we can use that value later to determine exactly where through the cube the terrain passes. Because right now we're just putting it smack bang in the middle. But it helps if you want that nice smooth terrain like what 7 Days to Die does. You need to know exactly where through the cube it passes, and we can use these values. So that's why we want those values correct if in fact the terrain is going through this cube. However, say for this cube down here, it doesn't matter because this cube is far enough below the terrain that it doesn't matter how far it is at all. So for this value, like this value here is going to be 0.3 because it shares a point with this one, but this one down here can just be 0. So then finally, we're just going to say terrain map x, y, z equals point, and that's it for that function. So we'll just collapse that. So the next thing we're going to do is go back to our match cube function, and we're going to change the parameters it takes in. So right now we're passing in an index. We don't want to be passing in an index. We want to pass in the data of the given cube that we're looking at, and we want it to calculate its own index. So we're going to change this to an array, which we're going to call cube, and then we're going to create a config index int up here, which we'll set to 0 by default. And then we need a way of getting the configuration. And for that, we're going to create a new function. So this function is going to be, it's going to return an int. It's going to be called getCubeConfiguration. And it will also take in a float, which we're going to call cube. And the cube is going to be an array of floats that represent these values that, in here, these values that we set here. So each point of a given cube, and it's looking at these values. So we're going to start off by creating a int that we can modify. Configuration index equals 0. And then we're going to loop through each of these values that we've passed in the cube. That is less than 8 because there are 8 corners. So now we're going to say if cube I is greater than terrain surface, that's a 0.5 value here, and this is where we use a bit of dirty bit magic. So if it's above the surface, configuration index straight line equals, I'm sorry, I've forgotten the name of the operand, 1, and I've forgotten the name of all of these operands, but I can tell you what they do. Basically, right, so let's just close all this off first. Then once we've done that, we are returning configuration index. Right, so here's what's going on here. We're starting off with 0. So if you remember each one of our corners has a value assigned to it, but more than that, you can think of it as a bool as well. So I mean, we're not storing it as a bool, but basically if, for example, this one is above the terrain, so it could be 0.6 because our terrain surface is 0.5, and this one is below the terrain, 0.2. What you can also think of is this one as true and this one as false, or vice versa. So this is doing that check. Now, as you remember, we have this massive array of triangles here, and there are 256 of these. There are also 256 combinations in a byte of, when I say combinations, I mean combinations of bits. So you have 000 000 is a byte that is the bits that represents the byte 0. And I'm not going to be able to remember any of what they are off the top of my head. Oh, sorry, I can remember 32. So basically, if you imagine that's a byte, that byte represents 0, which is what we set it to by default. So what this is doing is it's sticking a 1 into the actual bit value or byte value. I'm sorry if I'm using the wrong words. And it's sticking it at the position that I is determined. So if we're looking at the very first corner, it's going to be putting a 1 there. If we're looking at the third corner, it's going to be putting a 1 there. Or I guess the third corner is technically the fourth corner because we start at 0. But yeah, anyway, so that's what that's doing. So we get a bit value or a byte value, a bit byte value from our cube, from our floats in this cube, based on whether they are above or below the terrain surface. And then at the end of it, because we've essentially reset this value based on the bits. So we're setting this value, but we're setting it at bit level. So for example, I said 00000 equals 0, but 0010000, for example, equals 32. And then if we go down here, 32 is like one of these. So now we've got this function, we can go back to here. And instead of setting this to 0, we can set it to get cube configuration, and we're just going to pass in that cube. So now we just need to try that out. So if we go to our, so we're going to get rid of this because we're not doing it that way anymore. We'll just keep everything in start. Our terrain map needs to be +1. Otherwise we're going to get an index out of range error. And then we're just going to say populate terrain map. Now the last thing that we need to do is we need to actually create our mesh. So we'll do one last function, and we're going to call it create mesh data. And if I just steal these from here because I'm lazy and I can't type. So for each position in our and this time we don't need to be adding the +1. This is looking at the cubes, not the points. So this is the actual height and width of the area. I mean, you can think of it as a chunk, but we haven't got that far yet. So the first thing we're going to do is create that cube. It's going to equal a new float of 8, because that's how many corners are in a cube. And then we're going to say for int I equals 0, I is less than 8, I plus. And then we're going to get the current corner from the one table that we haven't used yet, which is called corner table. And it's, as you can see, it is a vector3 int list or array. So we'll just call this corner equals new vector3 int x, y, z plus corner table, and we pass in the current corner that we are looking at. And then we can just say cube I equals terrain map corner.x, corner.y, corner.z. And now, because our terrain map is one larger than our height and width, when this goes to check the outer corner, we don't get a null reference exception or an index out of bounds or anything like that. And then we march cube, and we're going to pass in our new vector3 x, y, z, and then we pass in our cube. And then if we go back up to here, we're going to say create mesh data, and then finally build mesh, and then we cross our fingers and see if it works. And there we go, we have some terrain. That worked out quite well. So as you can see, it's very isometric, very blocky. We're going to go over making it nice and smooth and a bit more realistic looking in terms of shape in the next video. But this is all modifiable. So if I were to go back in here, and where do we have populate voxel map? What did I do with that? Populate terrain map, sorry. And what we could just do is say if x, let's say x is equal to 4 and z is equal to 5, just pulling numbers out of thin air, then point equals 0. So we can see we have a bit sticking up. So if I change this to 1, now we should have a hole in the ground at that same spot, and there it is. And also, you might now, for people who've played 7 Days to Die and wondered why the terrain acts kind of weird compared to the blocks of the construction, like when you're building houses and stuff, it's because of how this mesh is drawn. That's just the way marching cubes works, unfortunately. But that's why you get the kind of diamond shape rather than the cubes. So, you know, make a bit of a larger hole if you want. So we could do if x is greater than 4 and x is less than 9. Z is greater than, let's say, 10, and Z is less than 16. So now we should have a big hole in the ground, basically. And there it is. And just for one last test, we'll also check and Y is greater than 1. So now we should have a hole in the ground with a floor. And you can see it all works. And then we'll go over destructing the terrain in possibly the third video. So we'll get a simple setup going where you can just click on the terrain and it will modify it on the fly. But for the next one, I want to try and get nice smooth terrain going. Possibly some texture, and I'll have to see about that because I don't know how that might be a video of its own. But yeah, so that is it for this video. We've got the basics of our terrain going, and like we'll make it look a bit nicer in the next video. Let me know what you think of this video. Like I say, I'm going to continue it for a bit regardless of whether it's popular or not, but obviously if I get 10 videos in and nobody's watching it, I'll have to rethink whether I really want to do it. But as I say, Minecraft people, don't worry, Minecraft videos will be unaffected by this. I'm not replacing or ditching the Minecraft series. That's all for now. Thank you for watching. You're all amazing. Bye-bye. No, not bye-bye, because I haven't said thank you to my amazing Patreons. Thank you, Patreons. Thank you. Especially you, Professor DJ.